Welcome back to Backspace Academy. So in this lesson I'm going to run through Amazon DynamoDB and look at the DynamoDB components being tables, items, attributes and primary keys. We'll then look at secondary indexes. We'll look at queries and scan operations and the difference between the two. We'll look at the ways in which we can update data, and we'll look at provision throughput and DynamoDB streams and DynamoDB triggers. So DynamoDB, it's AWS's managed NoSQL database service. It supports storing, querying and updating of documents, and the data, it's stored in a JSON-like format or a JavaScript object notation-like format. So developers will like that, and we'll look at in the lab, we'll see exactly how to bring in a JSON file and how easy that is to do. So it's in that sort of format and quite understandable for a developer. It consists of tables, items and attributes, and we can also define secondary indexes on our data to speed up the querying of that data. The advantages of DynamoDB is that it scales seamlessly, and it does that simply through API and CLI calls, and so you can change the provision throughput of your database as simply as just doing a call. So there's not much involved in that, and it's a very, very quick process. So it does scale far quicker than you would see in a normal relational database. You can query on any attribute or column using secondary indexes. It supports cross-region replication and does that quite easily. It's schemaless like NoSQL database, like most NoSQL databases. It supports strong consistency on reads. It has something called atomic counters. We'll discuss that in a sec. And there's also a downloadable version, so great for developers if they want to play around with this on their development environment, on their PC or whatever. They can download that and run that locally on their PC. So it's a pretty handy thing to have. So the difference between NoSQL and SQL. So there is a big push nowadays, and there's a growing popularity in NoSQL databases, and SQL has been pretty stagnant in uptake over the last couple of years, and NoSQL has really grown and taken off and starting to catch up, and will possibly eventually overtake SQL databases. So SQL databases have been popular for quite some time because in the past storage was expensive, and so SQL optimized our storage, so we didn't waste storage. So everything that was there needed to be there, and there's nothing duplicated, and there's no wasted storage whatsoever. Whereas a NoSQL database, it compromises storage, but it compromises it for the benefit of speed. So there's not a major compromise on storage. It's not like you're doubling your database size, but you know they can be slightly bigger than a SQL database, but they're significantly faster as a result. So the SQL data is normalized, or it's a relational database. So you might have a client database with individual people's records in that, and they might work for a company. So they've got a company ID for that company, and so that would have a relationship to another table called companies, and the primary key of that table would be the company ID. And so that's how we create that normalized data, and we don't have any wasted space. Only what needs to be there is there. NoSQL, it's denormalized, so we could have in the one table all of that information, and it would be in a hierarchical fashion. So it does create, it does waste a little bit of space, but it's significantly faster by doing that. Now SQL data has joins and rules, so that creates a lot of overhead for a SQL database. So when you break that away and you take away those joins and rules that need to be handled by the SQL database, you're freeing up a lot of compute capacity there, and so NoSQL databases, as a result, are significantly faster. The downside is that the SQL language is very rich, and it's been around for a long time and quite an advanced language. So NoSQL, you're really just relying upon simple queries and scans to get the information you want. You don't have that same level of richness that a SQL language has. But that said, when NoSQL databases are combined with something like AWS EMR, which is AWS's Hadoop Elastic MapReduce implementation, or if it's combined with Elasticsearch, AWS Elasticsearch, that will allow you to have an SQL-like language which is rich, and you can do some very complex queries on that data as you would with a SQL database, but without having that overhead on the original database. So something to consider if you really need that rich SQL language. You can also look at Hadoop or Elasticsearch to make that happen. So SQL scales vertically, whereas NoSQL scales horizontally. So if you want to create more capacity in a SQL database, you generally need to get a bigger database. Whereas NoSQL, it scales out horizontally, so you can quite easily scale out to quite large sizes and pull that back in quite easily. So SQL is suitable for OLAP, online analytical processing, whereas NoSQL, it's suitable for online transaction processing. And that's because of the rich language and the joins and rules that SQL has. It lends itself well to analytical processing. But again, if you take advantage of other services like Hadoop, that can fill that gap for you. So the components of a DynamoDB database are tables, items, attributes, and primary keys. So tables are a collection of data. So you'd have a customers table. And so within that customers table, you would have items. Now, items are similar to rows or records in a relational database. And then you would have attributes. So items would have attributes. So an individual customer inside of that customer table would have a customer ID. They'd have a first name and a last name. And tables, they must define a primary key as their unique identifier of their items. So each item would have a customer ID in that customer table as an example of a primary key. Now, primary keys can be just one, as in a partition or hash key, or they can be partition and sort, so a hash and RAID. So there's two types of primary keys that you can use in your tables. So just looking here on the right hand side there, it's got a diagram of a books database. So this could be a bookstore or a library or whatever. So in our bookstore or our library, we've got individual books, items. Okay, so we've got a books table, and inside of that we've got, and we see here, we've got two books that I'm showing. So each book will have attributes. So it'll have a price, it'll have a title, it'll have authors, it'll have dimensions. So they're the attributes of that book, and all those books will have, all of those items being books will have individual attributes. So that's how that works, and that's the components of DynamoDB that you need to understand that terminology. So we can also create secondary indexes. So they let us query the data using an alternate key in addition to the primary key. So it can speed up things if we're looking for data, and we can search upon not just the primary key. So just say, for example, we wanted to search not only on ISBN but on title and authors, we could set up a secondary index around that which would contain that information. So it would be basically a subset of that original database. So you can define up to 5 global secondary indexes and 5 local secondary indexes, and we'll talk about the difference in the next slide, for a total of 10. So that's a total of 10. You can't have 10 global or 10 secondary. You can only have 5 of each for a total of 10. And you can specify which attributes will be copied or projected into that secondary index. Now, they're not essential, but they are recommended because they do improve your flexibility and speed of querying. So if you've got a large database, you should definitely start looking at secondary indexes. So the difference between a local and global secondary index. So a local secondary index has the same partition or hash key as the table. So we can see here up the top there in green, we've got the ISBN, which is the same as before, but they have a different sort or range key as a table. So if we wanted to create an index where we could quickly find the authors for an ISBN, that's the way we would set up that that local secondary index. We also have global secondary indexes, so they have a partition and sort key, or hash and range key, that can be different from the original table. So we look there, we've got a global secondary index down the bottom there, and we're using the title as our partition key and the author as a range. So we can search on title and find the authors quite quickly there by setting up a global secondary index like that. So there are two types of ways of getting information or receiving information from your database, and that is through a query or a scan. So a query is more recommended and is generally more efficient than a scan operation. So it only searches for a specific range of keys that satisfy a given set of conditions. So unlike a scan that scans everything, the whole table, it only scans a specific range of keys and that satisfy those key conditions. After that, the results can be filtered again, and then that query can be eventually, or is by default eventually consistent, but you can also request a strongly consistent read. Now, scans are slower, and the larger the data set, the slower the response is going to be from a scan. So if you've got a large data set, make sure that you use queries rather than scans. So they scan the entire table or the entire secondary index and then filter the results afterwards. So they don't specify a range of keys. They scan the entire table and then filter afterwards. So very compute intensive, so you don't want to use them too often unless you've got small databases. They're eventually consistent, but a consistent read set to true will return results at the time the scan started. So if consistent read set to true and you send off a call with a scan, the results that will return will be the results at the time the scan started. So one thing to consider is that will consume twice the read capacity units over an eventually consistent read. Another thing is that we can look at how we update our data. So we have two ways of doing that. So we've got atomic counters. Now, what they are is that they're very good for non-critical counter applications. So eventually, if you had a site visits counter, so a hit counter on your website, it doesn't matter if that's out by 1 or 2 or whatever. It's really just there to start collecting the thousands. It's not critical. Okay, so basically the way they work is that you would do an update item operation, and that would increment or decrement the value of an attribute without interfering with any other write requests. So you're basically sending that out and getting a response straight back, and it just does what it's got to do without holding up your application. So it's a very quick way of just saying, right, okay, update this counter or decrement this counter, and then you move on. So it's good for non-critical counter applications like a visits counter. Now, writes are applied in the order they are received. Now, the counter will increment each time you call an update item. So every time you do an API call update item, it will increment. Now, it will do that whether or not the call was successful. So there is a possibility you might actually have a call not successful, and then you end up doubling up on the counter. So if we're looking at situations where it might be a financial transaction or something like that, then you definitely don't want to use atomic counters for where the information is highly critical like that. So the other way is conditional updates, which you would use for that sort of more critical data. So you would use return values parameter of update item. And if you want to get the item attributes as they appeared either before or after they were updated. So you set that returns value parameter depending on what you want, either before or after it was updated. And so they're very good for critical applications such as finance and ERP. So again, the provision throughput, DynamoDB, it scales really well. It scales very, very easily. And so That provision throughput you can change, and you can change it very easily. So we need to understand what is provision throughput, and so certainly when we're designing these solution architects would certainly need to understand, how we design out the provision throughput to start with. So that provision throughput will be specified separately for tables and indexes. So the provision throughput for a table will be different, or could be different, may not be, but it will be specified separately from the indexes, so they have their own provision throughput specification. And customers, you can purchase reserved capacity. So if you know what your demand is going to be over long term, then you can reserve that capacity and get cost savings for that. So read capacity units. So they are calculated as one read capacity unit represents one strongly consistent read per second, or two eventually consistent reads per second. And that's for items up to 4K in size. So if it's over 4K in size, then you're going to need, if it's between 4 and 8, then you're going to need 2 read capacity units, not 1. So a write capacity unit, so one write capacity unit represents one write per second for items up to 1K in size. So secondary indexes, if you've got those, they will require additional capacity units when you're writing. So one for writing to the table and another one for writing to the index. So just remember that if you've got secondary indexes, you need to have double the write capacity units that you'll be provisioning. So you need to provision it for both the main table and for the secondary index. So just some examples here, and you need to understand how this, it does get a little bit confusing, but once you've done a few of them, it's pretty common sense. So let's have a look here. So we've got a 5K item size, and we want to do 50. We require 50 eventually consistent reads per second of 5 kilogram items. So 5 kilobyte items. So that would be 5 divided by 4. Okay, so we've got 4. Well, each requires that each item is a maximum of 4K. So we need 2 of those. Okay, so we need over 4. So we need 2 of them because it's 5K item in size. So that's 5 divided by 4 rounded up. So that's 2. And then we need, these are eventually consistent reads. So we need 2 eventually consistent reads per read capacity unit. So we divide that by 50 divided by 2, and so that gives us 50 as our provision throughput that we require. So let's have a look at another one. So we've got here 2 KB in size, and it requires 50 strongly consistent reads per second. Okay, so this is strongly consistent. So we're going to need double the amount of capacity that we would need over a eventually consistent read. So again, it's divided by 4, so 2 divided by 4 and rounded up, so that's 1. So we need 1 to start with, multiplied by 50 reads per second, divided by 1, because there is 1 strongly consistent read required per read capacity unit. So that comes to 50. So if that was an eventually consistent read, that would be 50 divided by 2, because you need less of them for eventually consistent reads. So it's 50 again. So let's have a look at writes. So provisioned write capacity that we need. So we've got 10.5 KB in item size, and we want to get 50 required writes per second. So we obviously don't need to worry about eventually and strongly consistent reads, because these are writes. So it's 10.5 divided by 1. So the size is 1K, unlike reads, which is 4K, it's 1K for writes. So we have 10.5, and that rounded up is to 11. So 11 times 50, which is 550. So the writes are quite straightforward to work out. So the reads need a little bit more thinking, so you need to understand the difference between eventually consistent, which requires half the amount of capacity, as a strongly consistent reads per second. Now, DynamoDB streams, so they're a reasonably new introduction to DynamoDB. So they're an ordered flow of information about changes to items in a table. And what that consists of will be stream records, and they're created whenever an application creates, updates or deletes items in that table. So whenever you change something in a table, or if you delete some item, if you change the title of a book or whatever in that book's database, that will create a stream record, and that stream record will be assigned a sequence number, and so that sequence number will allow you to see which one came before. So if you're trying to look at different stream records, you can tell by the sequence number the order with which it was created. So stream records, they're organised into groups or shards of records. And the stream records within a shard are removed after 24 hours, so they're not there forever. But it's another thing that you can use for monitoring what is going on with your DynamoDB table. So another thing similar to, or it was introduced in a similar time around where streams were introduced, is DynamoDB triggers. And they're triggered by item level updates on a DynamoDB table. The way they work is that they don't trigger a CloudWatch alarm or anything like that. They invoke a Lambda function, and then that Lambda function can be used to do whatever you want it to do. So it can be used to, for example, I've just got a couple of examples there. It could be used to send an SNS notification by an email or something to say that some part of the database has been touched. So it's great for security purposes as well. So if you want to really monitor your data and make sure that if something changes, that is very important that you have a process in place that manages that. It could also just write to an S3 bucket and store some information there about that event. So you associate an AWS Lambda function to that stream on a DynamoDB table, and that's how that works. So it's so you rely upon that AWS Lambda function that you create to implement what you want to implement with it. So that's all we'll go through now on DynamoDB. You'll be looking a lot more into DynamoDB and in quite significant in-depth detail in all of the streams. In the Solutions Architect and SysOps Administrator, you'll be using the command line interface to import data, to update that data and change that data. You'll be using the console as well to create the database. And in the developers stream, you'll be using the Node.js software development kit, and you'll be interacting with DynamoDB to do a similar thing that you would do with the command line interface as well. So I'll look forward to you in the next lessons, but in the meantime, you have to understand this properly and make sure that you do before you move on to the labs. So I'll see you in the next lesson.